This is Dr. D. Govardhan, Professor in the Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, discussing on tutorial question bank, Module 5, Impulse Momentum and Mechanical Vibrations in engineering mechanics. Here the definition of impulse and momentum. Let us consider F1, F2, F3 and F4 are the forces acting on a body as shown in figure. Let R be the representing the resultant of all the system of forces which are acting on it, and the direction of the resultant force always acts in the direction in which the body is moving. Let U be the representing the initial velocity of the body. After time t seconds, it attains final velocity v as shown in figure by traveling a distance of s now. Now, according to the second law of motions, R is equal to m into A, where R represents the resultant of system of forces, m is the mass of the body, A is the acceleration with which it is moving now. The acceleration is here, it is defined as the rate of change of velocity. It is equal to v minus u divided by t now. Simply, it can be written as now A is equal to dv by dt now. So, from this equation, so R into deta is equal to, we can write it now, m into dv now. Since an integrating for the distance moved from A to B position, that is S now. So, R into dt, that nothing but time is taken 0 to t is equal to, the velocity also changes from initial velocity u to v as shown in figure now. Hence, it is equal to mv minus m u now. So, the integration of R dt is called impulse, that is the product of force and time now. The units are Newton second. Sometimes here now, if R is the constant now, then impulse is equal to, generally it is equal to R into d. That is the R into, if it is R is the constant now. So therefore, from this relation, so R into integration of R into deta is called impulse, which is equal to the mv minus mu. That is, it is called change in momentum now, where mv stands for the final momentum and mu is representing the initial momentum. That is, the impulse is equal to change in momentum, we can call it. Here, the force is also vector now, the impulse is also vector now. Hence, that body is, the impulse is act in the direction in which the body is moving now. Conservation of linear momentum. The momentum of a system in a linear direction means along the one direction we are taking now. That is along the x-axis. The moment of a system in a linear direction is always conserved. That is, the change in momentum is equal to 0, or in another words, the moving body, the momentum possessed by the body at initial stage is equal to the momentum possessed by the at final now. Or in another word, the change in momentum is equal to 0, or the momentum possessed by the body remains constant in linear directions. This law is called conservation of linear momentum. In other words, the total momentum of the system in a direction before collision is equal to the total momentum system after the collisions now. Here the impact, the word what we are saying now, it is nothing but collision is taking place. Before the collision, so what is the energy, that is the momentum possessed by the body is equal to the energy for momentum possessed by the body after the collisions. Hence, the initial momentum is equal to final momentum. Hence, here it is called the moment is not at all changed in a linear direction. So, this law is known as conservation of momentum. Mathematically, the total momentum of two bodies remains constant after their collisions, or in other words, in mutual actions. Here, when the two bodies are collided with each other, the momentum possessed by the two bodies before the collision should be equal to the momentum possessed by the body after the collisions according to the law of conservation of momentum. Let M1 and F2 represent the masses of the two bodies, and U1 and U2 represent the initial velocity of the body before the collisions, and V1 and V2 represent the velocity of the two bodies after the collisions. Assume all are moving in linear directions. According to the law of conservation of momentum, the momentum possessed by the bodies before the collisions M1 U1 plus M2 U2 should be equal to the sum of the momentum possessed by the bodies after the collisions M1 V1 plus M2 V2. If the two bodies are moving in different directions, no? Since a vector is the quantity, force is a vector quantity, as well as the momentum is also a vector quantity. Hence, the impulse which is in the x directions should be equal to the change in momentum along the x directions. Similarly, the impact in y directions is equal to the change in momentum in y directions. Now, the momentum will be vector as a momentum is the product of mass and velocity. Here we are taking the fx into dt, that is the component of force which is acting along the x directions from 1 and 2 multiplied by the time t dt, it is equal to the m into v2x minus v1x, which is also equal to now in y direction. So 1 to, that is the integration from 1 to 2, fi into dt is equal to m into v2y minus v1 y naught, where fx and fi representing the impulsive forces along the x direction or y direction respectively, and v1x and v2x it is representing the v1x and v2x represent the velocity of first and second bodies along the x directions, and v1 and v2y is representing the velocity of components in the y directions. Now, where f is representing the resultant force, which is equal to the under root of fx whole square plus fy whole square. Now, based on these equations, we are taking one problem here now. A football of mass 200 grams is at rest. A player kicks the ball which moves with a velocity of 20 meters per second at an angle of 30 degrees with respect to the ground level. Find the force exerted by the player on the ball. The duration takes 0.02 seconds now. Here the mass is given 200 grams. Here it is represented in terms of kgs, 0.2 kgs now. Duration of the strike equal to 0.02 seconds. Initially the ball is at rest. Hence the component of velocity along the x direction and y direction is equal to 0. That is v1x is equal to 0 and v1y is also equal to 0 now. After kicking, the ball is moving with a velocity of 20 meters per second at an angle of 30 degrees now. That is, here it is representing the direction in which the body is moving now. So it can be resolved into two components now. That is along the x direction, along the y direction. Here along the x direction is equal to, we can take it as in just v to x, it is equal along the x directions. Here v into cos, we can take it as 30 degrees now. That is equal to 20 into cos 30 degrees now. Similarly, along the y directions now, that is v to y, it is equal to v into sine 30 degrees, which is equal to 20 into sine 30 degrees now. So, this is nothing but velocity is resolved into two components now. Assume just fx and fy representing the component of forces acting along the x direction and y directions. Then the momentum, impulse momentum equations in the x direction is equal to fx into t, that is the impulse in the x direction is equal to change in momentum in x directions, which is equal to m into v2x minus v1x now. Since v1x is equal to 0, it is equal to 0, the remaining content is equal to fx into 0.02 equal to 0.2 into 20 cos 30 minus 0 now. From this relationship, we got fx is equal to 173.2 newtons. Similarly, in y directions now, the component of impulse is equal to Fy into t equal to change in momentum in y directions m into v2y minus v1y. Since the ball is at initially at rest to, hence v1y is equal to 0. From this relationship we got to v2y is equal to 20 into sine 30 and v1y is equal to 0. On substituting these two values in the equations, we got Fy into time is equal to 0.02 is equal to 0.2 into 20 sine 30 minus 0 now. On substituting sine 30 values in the equations, we got fx is equal to 0.2 into 20 sine 30. Sine 30 is equal to 1 by 2 divided by time is equal to 0.02. On simplifications, we got this value is equal to 100 newtons. So, the resultant impulse force exerted on the ball is given by total force, which is equal to under root of fx whole square plus fy whole square. That is the component of forces acting along the x direction and y directions, which is equal to under root of 173.2 whole square plus 100 whole square. It is equal to 199.9 and approximately it is equal to 200 newtons now. So, the direction of force is given by, that is a theta is equal to, you can take it as tan inverse of Fy divided by Fx 100 divided by 170. Okay, by using the relations we can determine both the magnitude and direction of the force now. But here the body is acting, the body is moving already in the direction of 30 degrees with the horizontal. Hence, the resultant of that impulse force acts in the same directions. Problem number 2. The figure 2 shows a ball of mass 125 grams moving in horizontal directions towards the bat with a velocity of 20 meters per second. The ball attained a velocity of 32 meters per second at an angle of 30 degrees with respect to x-axis when hit by a bat. Find the impulsive force exerted by the bat on the ball if the duration of the strike is 0.025 seconds. The given data in the problems, the mass of the ball is given 125 grams. It is converted into kgs, which is equal to 0.125 kgs. The initial velocity, that is before the ball hitting the bat now, is given by, it is in horizontal. So, v1 is equal to 20 meters per second. Here, since the word is given, it is in horizontal. When the velocity, initial velocity results into two components, the component of velocity in the x direction is equal to v1x is equal to 20 meters per second, and v1y is equal to 0, that is the y component is equal to 0. So after hitting, the final velocity is given 32 meters per second at an angle of 30 degrees. Again, it is now resolved into two components now. That is v2x and v2y now. Here, initial velocity of the ball is, it is moving toward the right hand side now. But after hitting, the ball is moving again toward the left hand side, as shown in figure. Hence, the direction of motion of ball after hitting is treated as a negative directions, because it is the opposite directions in which the body moved earlier now. Hence, v2x is equal to minus of 32 cos 30, and v2y, it is moving upward directions, it is taken as positive. v2y is equal to 32 sin 30 degrees now. Duration of the stroke is equal to t is equal to 0.025 seconds, and writing impulsive momentum equation along the x direction and y directions. Along the x directions, the impulse is equal to fx into t is equal to change in momentum is equal to m into v2x minus v1x now. So from this relations, we got fx into 0.025, it is equal to 0.125, that is mass of the ball. The velocity is given minus 32 cos 30 minus 20 degrees now. That is v2x minus v1x now. So from this relationship, we got fx is equal to 0.125 minus of minus 32 cos 30 minus 20 divided by 0.025, that's the time, which is equal to minus of 238.56 newtons. Similarly, for y direction, so Fy into t is equal to m into v2y minus v1y. Here, f into t is equal to 0.025 equal to 0.125, that is the mass of the ball. The component of velocity, final velocity 32 sin 30 positive minus 0, that is the vertical component of velocity of the ball before hitting, it is equal to 0. From this relationship, we got fx is equal to 0.125 into 32 sin 30 divided by 0.025. So from this relationship, we got Fy is equal to 80 newtons. Okay, the resultant impulse force exerted on the ball is given by F is equal to under root of Fx whole square plus Fy whole square. We got it is equal to 251.6 newtons. Now, I am taking the problems in mechanical vibrations, time period and frequency for various pendulums. Now, I am considering the ball or an object. It is moving along the circumference of the circle of radius as shown in figure in counterclockwise directions or anti-clockwise directions. Just after time t, the displacement of the rotating body is equal to theta. Assume it is at a p position. Okay, it's a projection, that is the projection of point p, and vertical diameter, that is y dash, is at n position. When the point p is moving along the circumference of the circle, that is x to y, its projections on vertical diameter, it also starts moving from O to Y position. Again from Y to X dash when body is moving along the circumference now. Again its projection comes to Y to O position now. Similarly X to Y dash position, so O to Y dash position. When the object is moving Y dash to X dash position now, again its projections goes from Y dash to O position. Or in other words, when the object is moving along the circumference of the circle for one complete revolution, its projection vertical diameter also oscillates one cycle now. Here at a time t, assume it is at p position now. Assume x and y is representing its coordinates now. So yn is equal to y according to these equations now. Then y is equal to, we can write it as o1 equal to, it is equal to r sin theta, which is equal to r into sin omega t, where theta is representing angular displacement, which is equal to the product of angular velocity multiplied by the time taken now. That is sin omega t now. So integrating the above equations once now, that is dy by dt is equal to wr into cos omega t. From this relationship we got to here now, v is equal to omega into r as usually there, and cos omega t is equal to 1 minus sin square omega t. It can be written as now omega into r into under root of 1 minus sin omega t is equal to y by r, 1 minus y by r whole square, or it is equal to v is equal to omega into under root of r square minus y square. Okay, from this relationship we can determine the velocity of the oscillating body on horizontal. It is obtained by using the relationship v is equal to omega into r square minus y square, where v is representing velocity at a distance of y from the center of the circle. Now again differentiating equation number second with respect to the y, d2y by dt square is equal to minus of omega r square sin omega t now. From this relationship a is equal to d2y by dt square is equal to acceleration, which is equal to minus of omega r square into sin omega t is equal to, we can write it as a y position. So from this relationship, when the body is accelerating now, oscillating along the vertical diameter, its acceleration is always proportional to its displacement, that is the y, and it acts always in the opposite direction which the body is moving, or in other words, it is acting toward the equilibrium position. That is the center of the circle now. Okay, based on these two equations, we have to determine the frequency as well as the time period of a object when it is oscillating along the vertical diameter of the circle. Now I am taking a body moving with simple harmonic motions as an amplitude of 1 meter, and the period of complete oscillation is 2 seconds. What will be the velocity and the acceleration of the body after 0.4 seconds from the extreme position? Okay, given data is given, the amplitude is given now, it is equal to 1 meter. Periodic time is equal to t is equal to 2 seconds. And the time taken by the body from extreme position is equal to 0.4 seconds. This is the given data in the problem. Now let O be the position of the center of the body when the body is moving along the circumference circle with a uniform angular velocity omega. After time t seconds, assume it is occupied new positions p as shown in figure. It is given. Let P is representing the position of the object. When it is coming back from its amplitude just y to this end position within 0.4 seconds. Therefore, the time required by the body to travel from y to P position now, it is equal to 0.4 seconds now. So the time required the body to travel O to Y is equal to O to Y is equal to 1/4 multiplied by the time period, because complete oscillation nothing but it is coming from Y dash to Y, again Y to Y dash now. But here we are taking O to Y, hence it is nothing but 1/4 of its time period. It is equal to, time period is given 2 seconds, 1/4 into 2 is equal to 0.5 seconds. The time required the body to travel from O to N position is equal to 0.5 minus 0.4. It is equal to 0.1 seconds now. So the angular velocity of the body is equal to 2 pi by t is equal to 2 pi divided by t is equal to time period 2 seconds is given, which is equal to pi now. The displacement of the body after 0.4 seconds from the extreme position, or in other words 0.1 second from the mean position, it is equal to y is equal to r cos omega t now. It is equal to 1 into cos pi into omega t. Now omega is equal to angular velocity that is already determined, its value is equal to pi into t is equal to 0.1. It is equal to 0.95 meters. The velocity of the body is equal to v is equal to omega into r square minus y square. From this relationship we got to pi into under root of 1 square minus y is equal to, already we got 0.95 whole square. It is equal to 0.98 meters per second. The acceleration of the body, it is equal to a is equal to omega square y now, where omega is representing the angular velocity with which the body is moving. Y is the position of its projections on vertical diameter. Already we determined this equation, which is equal to pi square into 0.95 equal to 9.38 meter per second square. But its directions are always acts towards its equilibrium position, that is the center of the circle. Now we are considering now simple pendulum. The simple pendulum, it consists of a bob, that is the weight, it is connected at one end, other end is suspended from the ceiling, that vertically in downward directions. Here according to this figure, O A dash is representing the initial position of the bob. Here L is representing the length of the string, and M is representing the mass of the bob that is suspended at A as shown in figure now. Now after giving small displacement from A and released, it executes vibrations. These vibrations are called here now natural vibrations, because the force is not at all acting on it in every cycle now. The time period for oscillating body is given by Tp is equal to 2 pi by omega. For the simple pendulum, it is equal to 2 pi into under root of L by G now. One beat means it is half of the oscillations. It is equal to pi into under root of L by G now. If a pendulum which executes 1 beat per second now, then type of pendulum is called seconds pendulum. Okay, based on that above equations, we are having some important problem here now. A simple pendulum of amplitude 4 degrees performs 24 oscillations in 1 second. Find first part A, the length of the pendulum. B, the maximum acceleration of the bob. C, the maximum linear velocity of the bob. And D, maximum angular velocity of the bob. So the given data in the problem is theta is equal to 4 degrees is given now. Theta is equal to 4 now. So here the amplitude is equal to angle equal to, which is equal to, in terms of radians, 4 into pi by 180. That is in terms of in radians. The frequency is given now. That is, it performs 24 oscillations in 1 minute now. And so here frequency is equal to number of oscillations per second. So that is a 24 by 60 now. Length of the pendulum L, assume just L is representing the length of the pendulum. The time period for the oscillation is equal to, it is the reciprocal of frequency, which is equal to 60 divided by 24, because frequency we have taken, it is equal to number of revolutions per oscillation per minute, that is a 24 by 60 now. Hence, time period is equal to, it is equal to reciprocal of frequency, which is equal to 60 divided by 24 now. So 60 divided by 24 is equal to 2.5 seconds. So the time period for one oscillation is equal to, it is given by, time period is equal to 2 pi into under root of L by G. So from this relationship we got squaring on both sides, on simplification we are getting 2.5 nothing but 26.25, it is equal to 2 pi whole square into L divided by 9.8 now. On simplifications we got L is equal to 26.25 into 9.8 divided by 2 pi whole square, which is equal to 1.255 meters now. That is the length of the pendulum, that is completed. B2, maximum linear acceleration of the bob. The maximum linear acceleration of the bob takes place when it is in extreme position now. So the displacement of the bob is equal to arc AC, it is equal to maximum displacement is equal to AC, which is equal to OC into theta, which is equal to 1.55, that is the length of the pendulum is given. Theta is nothing but in radians we are expressing, it is equal to 4 pi divided by 180, which is equal to 0.108 now in radians. Angular velocity is equal to 2 pi by t now. Here it is equal to 2 pi divided by 2.5, which is equal to 2.51 radians per seconds now. The maximum linear acceleration of the bob is equal to A maximum is equal to W square into AC, that is nothing but where Y value displacement is maximum, the acceleration, the magnitude of acceleration also maximum, it is equal to W square into AC, which is equal to 2.51 whole square into 0.108, which is equal to 0.68 meters per second square now. The maximum linear velocity of the bob is equal to W into AC, which is equal to 2.51 into 0.108, which is equal to 0.27 meter per second. Maximum angular velocity of the bob is equal to linear velocity divided by the radius, that is the length of the pendulum, 0.27 divided by 1.55, which is equal to 0.174 radians per second. So these problems, it can be solved by using the relations what we discussed in a previous figure. Now compound pendulum, a uniform straight rod of length 600 mm and mass 250 grams is smoothly provided about the point, smoothly pivoted about a point which is a 40 mm from one end. Find the period of small oscillations about the pivot if the rod can turn freely in a vertical plane. Okay, the given that in the problem is called length of the rod is given, that is 600 mm. In terms of meters, it is equal to 0.6 meters. Mass of the rod is equal to 250 grams, which is equal to 0.25 kg. The distance between the point of suspension and the center of gravity of the body. Here, the center of gravity always lies at its center. That means from one end position, it is at a distance of 300 mm. So the distance between the point of suspension and center of gravity, it is equal to 300 minus 40, because it is suspended 40 mm from one end is given. That means this is equal to how much it is, according to the problem, it is equal to 40. So the distance between OG is equal to 300 minus 40, which is equal to 260 mm, or it is equal to 0.26 meters. The mass moment of inertia of the rod about the pivot G, it is equal to 0.25 into 0.3 whole square divided by 3 now. So which is equal to 0.0244 kg meter square now. The period of small oscillation is equal to 2 pi under root of I naught divided by mgh, where I naught is representing the mass moment of inertia of the oscillating body. mgh, it is nothing but mg is representing weight, where h is representing here now 0.6 now. That is the length. It is equal to under root 2 pi into under root of I naught is equal to that moment of inertia about its CG, is equal to 0.0244 divided by mgh. M is equal to mass of the pendulum 0.25 into 9.8 into 0.6 now, which is equal to 1.23 seconds. Okay, torsional pendulum. A torsional pendulum consists of a constant. It is also called shaft now. Generally, it is having negligible weight, and the shaft is fixed to the ceiling. It is freely suspended. At the bottom of the shaft, the rotated disc is attached to it. It is having W weight now. Generally, the weight of the constants, generally it is negligible when comparing with the mass suspended at its end. This body, when it is giving turning moment, turning force, just it will oscillate to and fro, twisting and untwisting with respect to the axis. That is, when it is oscillation taking place, generally torsional stresses are induced in it. So, here problem, it is a shaft of 100 mm diameter and 1 meter long, as one its end fixed and other end carries a disc of 500 kg at a radius of gyration of 450 mm. The modulus of rigidity for the shaft material is 80 giganewton meter square. Determine the frequency of torsional vibrations. Here D is equal to, that is diameter of the shaft is equal to 100 mm given, which is equal to 0.1 meters. The length of the shaft is equal to 1 meter. The mass suspended at the end of the shaft is equal to 500 kg. The radius of gyration of the pendulum is given 450 newtons, 450 mm, which is equal to 0.245 meters. The mass of rigidity for the materials is equal to 80 Gn per meter square, which is equal to 80 into 10 to the power of 9 Newton per meter square. Now, the polar moment of inertia of the shaft is equal to, generally it is represented as J, which is equal to pi by 32 d to the power of 4 now. So pi by 32, here d is equal to, is given now 100 mm. That is the diameter of the shaft is given 100 mm, which is equal to 0.1 meters, because we are converting all the dimensions into meters only, to the power of 4, which is equal to 9.82 into 10 to the power of minus 6 m to the power of 4 now. The Starner stiffness of the shaft is equal to Q is equal to Cj by L now. So which is equal to 80 into 10 to the power of 9. J is equal to 9.82 into 10 to the power of minus 6 divided by L is equal to, here given, 1 now. So by using this equation, we got 785.6 into 10 to the power of minus 6 Newton meter now. So this is called the torsional stiffness of the shaft, which is equal to Cj by L. By using the relationship, we determine its value is equal to 785.6 into 10 to the power of minus 6. Then the mass moment of inertia of the shaft is equal to mk square now. Here m is equal to that mass suspended, which is equal to 500 kg into 0.45, that is the radius of gyrations given square, which is equal to 101.25 kg meter square now. The frequency of torsional vibrations is equal to 1 by 2 pi under root of Q by I now, where Q is representing torsional stiffness and L is representing the, I is representing mass moment of inertia now. So I'm substituting the values now. This is nothing but here I 1 by 2 pi into under root of here 785.6 into 10 to the power of minus 6 divided by 101.25 now. So on simplifications, we got it is equal to 14 H now. That is 14 cycles per seconds. Now the problem related to the spring here now. A 4 kg mass hang at one end of helical spring and set vibrating vertically as shown in figure. The mass makes 2 vibrations per second. Determine the stiffness of the spring. The given data in the problem is that is mass of the suspended air at end position is given, the 4 kg. The frequency is equal to n is equal to 2 vibrations per second. Then it is equal to 2h. Let S be the representing the stiffness of the spring now. The periodic time is equal to, here it is equal to reciprocal of the frequency, that is 1 by n now, that is 1 by 2, which is equal to 0.5 seconds. But for the vibrating system, time period is equal to 2 pi under root of m by s now, which is equal to time period is equal to 0.5, 2 pi into, here m is representing the just mass suspended, here s is given now, stiffness of the spring now. From this relation squaring on both sides, we got to 0.5, it is nothing but 0.25, which is equal to 4 pi square 4 by s now. From this relation, we got s is equal to pi square divided by 0.25, it is equal to 631.6 Newton per minute. This is known as stiffness of the spring now. oscillation of spring and arrangement of springs now. Here, the two springs are connected in series as shown in figure. The first spring consists of stiffness is equal to S1 and the second spring consists of stiffness S2 as shown in figure. And the mass is suspended at the end of the second spring as shown in figure, and the first spring is suspended at the top. These two springs are connected together in series and mass is suspended at the lower end as shown in figure now. In this case, the equivalent spring constant is given by, assume if it is S, that is 1 by S is equal to 1 by S1 plus S2 now. Now problem is a block of 50 kg suspended by two springs connected in series hangs from the ceiling. It can move between the smooth vertical guides. The spring constants are 4 kilonewton meters and 6 kilonewton meters as shown in the figure. The block is pulled 40 mm down from its equilibrium position and then released. Determine period of vibrations, maximum velocity, and acceleration of the block when the block is supported by the spring connected in a series. The spring constant for the equivalent springs we have to determine by using the relations 1 by S is equal to 1 by S1 plus S2. Since the springs are connected each other in series, so which is equal to, on simplification we got to S1 plus S2 divided by S1 and S2, that is 4 plus 6 divided by 4 into 6, it is equal to 10 divided by 24. Finally we got S is equal to 2.4 kilonewton per meter now. The deflection of the spring is equal to, because when the mass is attached to it now, mg divided by S now, that is mass suspended to the stiffness of the spring now. Here mass suspended is equal to 50 kg is given now. Here 0.05 into 9.80 divided by 2.4, which is equal to 0.204 meters now. Here the mass suspended is here it is equal to 50 grams. It is equal to 0.05 kgs multiplied by 9.81 divided by 2.4, because we have taken all the units in MKS units now. The period of vibration is equal to T is equal to 2 pi into under root of delta by G now, where delta is representing the, that is the deflection of the spring now, which is equal to 2 pi into under root of 0.204 divided by 6.8, which is equal to 0.91 seconds. The angular velocity of the block is equal to, that is 2 pi by t, which is equal to 2 pi into t is equal to 0.91, which is equal to 6.9 radians per seconds. The maximum velocity is obtained. It is similar to the object when it is moving along the circumference circle we have taken earlier now. Its projections always oscillates along the vertical diameter. It is also treated as motion is the simple harmonic motion. The equation remains constant for all, which is equal to maximum velocity is equal to V maximum is equal to omega into R. Omega is equal to 6.9 into 0.204, which is equal to 0.276 meters per second. The maximum acceleration is equal to A max is equal to omega square into R now, that is 6.9 whole square into 0.04. It is equal to 1.9 meter per second square, but it always acts towards the equilibrium positions, or in other words, it is always acts in opposite direction the body is tends to move or moving. Here the springs are connected in parallel. In this case, the equivalent spring constant is equal to the sum of the spring constant S1 and S2. So the problem is a block of mass 50 grams now, suspended by two springs connected in series, hangs from the ceiling. It can move between the smooth vertical guides. The spring constants are 4 kilonewtons meter and 6 kilonewton meter as shown in the figure. The block is pulled 40 mm down from its position of equilibrium and then released. Determine period of vibrations, maximum velocity and acceleration of the block when the block is supported by the springs connected in parallel. Here first we have to determine the spring equivalent to spring constant when they are connected in series, which is equal to the sum of the spring constants of two springs, that is equal to S is equal to S1 plus S2, which is equal to 4 plus 6 equal to 10 now. The deflection of the spring is equal to, that is weight suspended to the, it is the ratio of weight suspended to the spring constant, mg by S, it is equal to 0.05 divided by, multiplied by 9.80 divided by 10 now. From this relations we got to, it is equal to 0.049 meters. The period of vibrations is equal to T is equal to under root of this 2 pi into under root of delta divided by G, which is equal to 2 pi into under root of 0.049 divided by 9.8, which is equal to 0.244 seconds. The angular velocity of the block is equal to omega, which is equal to 2 pi by T now. It is equal to 2 pi divided by 0.44, it is equal to 14.28 radians per second. The maximum velocity is equal to omega r now, where omega is equal to 14.28, that is angular velocity, into r is equal to radius of the circle, which is equal to 0.04. It is equal to 0.257 meter per second. The maximum acceleration is equal to minus omega square r, 14.28 into r is 14.28 whole square into 0.04, which is equal to 8.216 meter per second square. Okay, these are the problems we covered depending upon the syllabus which is given in mechanical vibrations. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.